Hi class, and welcome to your next video on determining health effects of pollutants. So the first thing we need to do is we need to assess the toxicity risk. We assess the toxicity of a pollutant by the dose at which the adverse effects are produced, which means at which someone is starting to show some kind of symptoms from a chemical or a toxin. And that dose is the amount of toxicant that enters the body of an exposed organism. But that dose is the amount that you're going to start seeing those symptoms, like a headache or a fever or stomachache. Something is going to start to show up. So we can measure these in several ways. They all involve quantitative measurement, which means they involve some kind of numerical data, since a milligram of the chemical all at once can have different effects than the same milligram spread over a day or a week. And consider this, that you're spreading this over the whole entire body, so the more a person weighs, the less that milligram effect, the less of the effect it will have on them, and the less the person weighs, the more effect a dose will have on them. So children need less of a dose than an adult. So response is the type and amount of damage that exposure to a particular dose causes. So a lethal dose is a dose that may cause death. It may be expressed in milligrams of a toxicant per kilogram of body weight, varying depending on the organism's age, sex, health, and metabolism. Now, this is also dependent on the type of toxicant that you're using. It may be dependent on the different chemicals and how much is needed for that particular toxicant. Lethal dose for humans are known through records of homicides and accidental poisonings. Obviously, we are not going to go and purposely lethally dose someone, but we are going to record what happened if a homicide or an accidental poisoning were to occur. So a sublethal dose then is something that may cause harm but not death. It is going to have some kind of dose response, which means you are going to see some kind of symptoms, but you are not necessarily going to, you're not going to see what you see with the lethal dose. Acute toxicity is one way to determine acute toxicity, one way to determine acute toxicity is to administer different sized doses to populations of laboratory animals and measure responses and use the data to predict the chemical effects on humans. Acute toxicity is the immediate toxin amount within one's bloodstream or within the animal's bloodstream. We usually look at this as lethal dose 50% or we call this LD50, the dose that is lethal to 50% of the population of test animals. This is usually reported in milligrams of chemical toxicant per kilogram of body weight. So remember, if we're talking about a rat or we're talking about a small mammal, it's going to be a lot different than it is for a human. There's an inverse relationship between LD50 and acute toxicity, meaning that a small LD50 is actually very toxic, but a large LD50 is not very toxic. The smaller the number, the more toxic the chemical. So the dose response curve in toxicology is a graph that shows the effects of the different doses on the population of test organisms. And I know you've seen a dose response curve when you did the toxicology problem set and you saw the dose response curve with alcohol. Well, there's dose response curves for all kinds of different toxicants and how they affect an organism. Scientists first test the effects of a high level of the toxicant doses, then work their way down to the threshold level. The high level is going to be the lethal dose, so death, and then the threshold level is the maximum dose that there's no measurable effect, or alternatively the minimum dose that produces a measurable effect. So you're not really going to see any symptoms, you're not going to have anything to know that there was a toxicant entering the organism at this level. So scientists assume that doses lower than the threshold are safe. So they assume that, and they report that as they report things with toxicants. So if we look at these dose response curves here, we can see that there is a threshold level, and we can see that there are different levels of toxicants. And you can see that based on the body weight, there are different threshold levels. And based on the threshold level, you can see it actually levels out very quickly as to the lethal dose. Now, a lot of times we talk about pollutants and cancer and all of these toxicants. Well, we want to know, are they really going to cause cancer? What is the risk of causing cancer? And we already looked at risk assessment, but we want to know, are these chemicals really going to cause us cancer? Well, cancer is something that is really feared in our society. For many years, it was the main effect evaluated in chemical risk assessment. But there's many other things that we need to evaluate in a chemical risk assessment. There are other diseases, birth defects, damage to immune system, nervous system, endocrine system, reproductive problems. There's all kinds of issues. Remember when we talked about the love canal and how those women were having all those reproductive issues? Well, they weren't getting cancer, but there were children being born with all these birth defects and women who were having miscarriages, and we were having all these reproductive issues, but yet it wasn't causing cancer. So we want to look at these environmental contaminants, but we also want to look and see, are they going to cause cancer? So the most common method of determining whether a chemical causes cancer is to expose groups of laboratory animals such as rats to various large doses of that chemical and count how many develop cancer at different levels. So we're going to have one group that is exposed to a very high rate of this chemical, another group that's exposed to a smaller rate, and another group that's exposed to a smaller rate. And we're going to determine the rates of cancer based on that. So a carcinogen, though, is any substance that causes cancer. So we have some problems with how we do this, though. We have to extrapolate from one species, the rats, to another, humans, and we have to extrapolate from high doses to low doses, which is uncertain, and we may overestimate or underestimate the toxicant's danger. So we really don't have a good way to test each chemical, because obviously it's unethical for us to be testing these chemicals on humans, but yet we cannot be testing them. We don't have another species to be testing them on, and so these high doses that we're exposing the rats to might be a low dose in human, but if we're exposing them to low doses in rats, they're really low doses in humans. So it becomes a bit of an issue. Scientists do not currently have a reliable way to determine whether exposure is too small of amounts of a substance to cause cancer in humans. There's no reliable way. Risk assessment of chemical mixtures. Humans are frequently exposed to various combinations of chemical compounds in the air we breathe, the food we eat, and the water we drink. Think about just the air you're breathing right now, or think about it if you were to step outside. There's car exhaust. There's smoke from people smoking cigarettes. There is nitrous oxide. There is ozone. There's all kinds of things interacting together. And then you're breathing that in. Well, the mixtures of the chemicals interact together, and they increase the complexity of the risk assessment. And the field that already has all those uncertainties, we don't know everything about it. We're just assessing that risk, which could be. So the chemical mixtures are going to interact in three ways. They're going to be additive, synergistic, or antagonistic. So let's look at what those are. So when they are additive, it's just the effect adding one to another. So it'd be like if a chemical compound has a toxicity of 1 and another has a toxicity of 1, the chemical compound now has a toxicity of 2. In a synergistic or synergy, the effect is greater and combined than what we would expect. So if one has a toxicity of 1, one has a toxicity of 1, the toxicity is going to be greater, so it would be 3 or 4. And with an antagonistic, it's going to be less than what we expected. So if they each have toxicity of 1, it's going to be 1 or less than 1 now. So children and chemical exposure. Children weigh less than adults and tend to interact more with their environments and are undergoing rapid internal changes as they grow. So lethal doses are smaller, but the chemicals are going to affect them more because they're smaller, they have smaller body masses, but they're still growing and changing, and these chemicals can change those changes more. The precautionary principle is the idea that new technologies, principles, or materials should not be adopted until there's strong evidence that they will not adversely affect human or environmental health. So it's the thought that an ounce of prevention is worth a pound of cure. If we prevent everything, then we don't even have to worry about a cure because there's no need for a cure. We've already prevented what might happen. So we should not introduce a new technology, practice, or material until it is demonstrated that the risk is small and the benefits outweigh the risk. One example of this is the European Union has a big problem with the beef that we use here in America. If you buy your beef from the grocery store, you get beef that was grown with growth hormone. And that growth hormone, we have no clue what it does to us. But we do know that it makes the cattle grow faster. Because we do not know what the risk with that is, the European Union has banned it since 1989. So they use the precautionary principle to say, nope, we're not even going to deal with that. So what I want you to do is I want you to complete the concept check numbers 1 through 5. You have a Wiley Plus. You need to log into your Wiley Plus and see what you need to do. Everyone has a changed Wiley Plus. I've changed it a little bit. So everyone's is not going to be the same. You're going to have different amounts that you can answer. You're going to have different amounts taken off for those answers based on what group I have put you in. 2. If you have questions about what I have done with your Wiley Plus, you need to ask. Your Wiley Plus is due by Thursday by the time you get to class. If you do not have this done, it is 25% off the first day. The next day, it's going to be 50%, and after that, I'm not going to accept it. So please complete your Wiley Plus. You're going to have time in class, okay? If Wiley counts it late, it's just going to become later and later, and I don't want this to snowball for you. So complete this, complete your Wiley, and get everything in on time.